The number is wrong, not slightly wrong, not a rounding error wrong. The age of the universe, the number you were taught in school, the number printed in every textbook, the number that anchors almost everything scientists tell you about where you came from, is now an open question, and the telescope that broke it is still sending back more evidence every single month. For most of your life, you have heard the same figure, 13.8 billion years. It gets repeated so often that it stopped sounding like a claim and started sounding like a fact of nature, something as solid as the boiling point of water. But that number was never observed. Nobody stood outside the universe with a stopwatch and pressed start at the beginning of time, and nobody ever will. The figure is the output of a model, a set of equations called lambda CDM, fed with data from a satellite, producing a result that only holds together if every assumption inside that model is correct. And in 2026, those assumptions are cracking in public, in peer-reviewed journals, in front of anyone willing to look past the headlines. Here is where it starts. In April 2026, an international group of astronomers called the H0 Distance Network published the most precise direct measurement ever made of how fast the universe is expanding right now in our cosmic neighborhood. They combined several independent methods, pulsating stars, dying giant stars, carbon stars, cross-checked across multiple telescopes, including Webb itself, and squeezed the uncertainty down to almost 1%. Their answer, the universe is expanding at 73.5 kilometers per second for every megaparsec of distance. That number on its own means nothing to most people. What matters is what it collides with. Because there is a second number calculated a completely different way, using the oldest light humans can observe, the faint glow left over from the beginning of everything. That method gives an expansion rate of about 67.4. Two teams, two rigorous techniques, two answers that refuse to agree, and as of this year, the gap is no longer just persistent. Scientists are openly using the word crisis to describe it. Not tension, not puzzle, crisis. Stop and actually sit with what that means. If you measured the length of a room with two different tape measures and got two different answers every single time, no matter how many times you tried, you would not assume the room is confused. You would assume one of your tape measures is broken, or that you don't actually understand what you're measuring. That is exactly the position cosmology is in right now. Except in this case, the room is the entire universe, and the tape measures are some of the most expensive, most carefully engineered instruments ever built by human beings. For a decade, the working assumption was that better data would fix this. Sharper images, larger samples, more careful calibration, and the gap would quietly close, the way most scientific disagreements eventually do. That is not what happened. Every time astronomers built a more precise instrument, the disagreement got sharper instead of softer. In 2023 and 2024, Webb pointed directly at the pulsating stars that anchor the local measurement, the ones critics said might be smudged together by crowding in older images. Webb had the resolution to settle it. It confirmed the earlier numbers. The tension did not dissolve, it hardened. Then, a completely separate technique using dying red giant stars and nearby galaxies as distance markers produced a third value, sitting uncomfortably between the other two, agreeing fully with neither. 3 independent roads into the same measurement, 3 refusals to meet at the same destination. Here is the part that should actually worry you, not comfort you. When scientists see a disagreement like this, what they secretly hope for is sloppiness. Large error bars, room for the numbers to eventually overlap once the noise is cleaned up. That hope is gone. The error bars have been shrinking for years, and in this most recent 2026 measurement, they shrank to about 1%, one of the tightest constraints ever achieved in the history of this field. Precision without agreement is the worst possible outcome for the old model, because it means the disagreement was never noise in the first place. It was signal. Something inside the standard picture of the universe is broken, and better tools are only making the fracture more visible, not less. Now hold that thought, because there is a second front in this story, and it comes from a completely different direction. Dark energy. The number 13.8 billion years does not stand alone. It depends on a universe made almost entirely of 2 ingredients nobody has ever directly detected. Roughly a quarter of everything is supposedly dark matter, invisible mass that bends light and holds galaxies together, but has never shown up in a single laboratory detector, despite decades of searching underground in tunnels shielded from cosmic rays, using instruments built specifically to catch it. Nothing. And nearly 70% of the universe is supposedly dark energy, an invisible force invented in 1998 purely because the expansion of the universe was accelerating and the equations needed something to explain why. It has no known particle, no laboratory signature. It exists because without it, the math does not match what telescopes see in the sky. For 25 years, the standard assumption was that dark energy is constant, a fixed background pressure that never changes, baked permanently into the fabric of space. That assumption is now the second thing cracking. The Dark Energy Spectroscopic Instrument, an enormous international survey that has mapped tens of millions of galaxies and quasars across billions of light years, has been releasing results since 2024 that keep pointing in the same uncomfortable direction. Dark energy may not be constant at all. It may be weakening over time. Their newest results, released through 2026 as they completed their planned 5-year map of the universe, strengthen this hint rather than erasing it. Independent teams analyzing the same data using different statistical approaches keep landing on evidence, sometimes reaching 3 to 4 sigma confidence, that the simplest version of dark energy, the one baked into every textbook diagram, does not fit the data as well as a version that evolves. If that holds up, and DESI is continuing observations specifically to find out, then the anchor holding the entire timeline in place is not fixed. It is loose. A universe where dark energy has always been constant produces one age. A universe where dark energy is evolving produces a different one. Change that single assumption and the number at the end of the calculation, the age you were taught in school, moves with it. And now the third front, the one that started this entire story, galaxies that should not exist yet. When the James Webb Space Telescope turned its mirror toward the deepest reaches of space, it was expected to find faint, chaotic smudges of early star formation, the messy first drafts of galaxies, thin and dim and disorganized, exactly what the standard model predicted for an infant universe barely a few 100 million years old. Instead, it found structure. Mature, massive, glowing galaxies sitting at distances so extreme that their light left them within the first few 100 million years after the beginning of everything. These are not supposed to exist. There has not been enough time, according to the standard timeline, for that much ordinary matter to collapse, ignite, and organize itself into anything that mature. The most recent research, published in April 2026, made the problem worse rather than better. Astronomers studying quiescent galaxies, ones that had already finished a major burst of star formation and gone quiet in the early universe, found that a large portion of their mass was hiding in faint, low-mass stars that are extremely hard to detect directly. When you account for that hidden mass properly, some of these early galaxies turn out to be even heavier than first estimated, by a factor of 3 or 4. In plain language, the impossible galaxies are not becoming less impossible as we study them more carefully. They are becoming more so. There is some nuance here, and an honest account has to include it. Not every early puzzle from Webb has survived scrutiny. A separate population of unusually oversized black holes found in the early universe, ones that seem to make up an impossible fraction of their host galaxy's total mass, has recently been partly explained. New analysis in 2026 suggests some of these black holes appeared overmassive, mainly because astronomers were seeing the brightest, most extreme examples first, a kind of selection bias, and that when you look at thousands of early galaxies together, rather than cherry-picking the most dramatic ones, the numbers move closer to what normal physics would predict. Other researchers have proposed that these black holes grew through unusually rapid hidden accretion that hides them from the X-ray searches astronomers normally use to weigh them. Science is doing exactly what it should do here, proposing explanations, testing them against more data, discarding the ones that fail. But the core problem, the one this entire story is about, has not gone away with any of those explanations. The massive quiescent galaxies remain massive. The Hubble tension remains, and has hardened into what researchers themselves are now calling a crisis rather than a puzzle. The hints of evolving dark energy have not disappeared with more data. They have strengthened. 3 separate lines of evidence, measured by 3 separate teams, using 3 separate methods, are all pointing away from the tidy, closed version of cosmology that most people still believe is settled science. Before going further, it helps to understand how anyone claims to know the age of something nobody was alive to witness in the first place, because none of these methods are as direct as they sound. Astronomers lean on 3 separate approaches, and none of them work like reading a number off a clock. The first uses the oldest light in existence, the faint radiation left behind from the moment the early universe first became transparent, and works backward using the current expansion rate to calculate how long ago that light was released. The second builds what is called a cosmic distance ladder, starting with nearby stars, whose distances can be measured directly through parallax, then using those to calibrate pulsating stars with predictable rhythms, then using those pulsating stars to calibrate exploding stars, bright enough to be seen across billions of light years. Every rung of that ladder depends entirely on the rung beneath it being correct, which means a small error near the bottom can quietly become an enormous error by the time you reach the top. The third approach looks at the oldest stars astronomers can identify, studies their chemical composition, and uses that to set a hard floor. Whatever the true age of the universe turns out to be, it cannot be younger than its own oldest stars. 3 separate methods, 3 separate sets of assumptions, and increasingly 3 accounts of the same event that refuse to fully agree with each other. There is also a strange population of objects Webb keeps finding that nobody fully understands yet, unofficially nicknamed little red dots. They are small, unexpectedly bright, and scattered throughout the early universe in far greater numbers than any simulation built before Webb's launch had predicted. Some researchers think they are baby versions of quasars, tiny galaxies feeding rapidly growing black holes at their centers. Others think they are extremely dense, compact bursts of star formation unlike anything seen in the nearby universe. Nobody has settled the debate yet, and every proposed model runs into the same underlying obstacle. There are simply too many of these objects for the standard timeline to comfortably explain, no matter which explanation for their nature turns out to be correct. Consider what this actually asks of you to accept. If the standard picture is right, it asks you to accept that a universe barely a few 100 million years old, one still in its infancy according to the official timeline, somehow assembled enormous, structured, chemically mature galaxies using nothing but the physics the standard model allows. Either the physics is incomplete, or the timeline is wrong, or both. There is no quiet third option that leaves everything exactly as it was taught. Think about what this means at a level closer to home, because this is not only an abstract argument about numbers on a chart. Every heavy element in your body, every atom of calcium in your bones, every atom of iron carrying oxygen through your blood was forged inside the extreme pressure of a dying star and scattered across space long before Earth ever formed. That process requires generations of stars living and dying in sequence, each one enriching the raw material for the next. If galaxies really were forming and maturing faster and earlier than the standard model expected, then the entire assembly line that eventually produced the atoms in your own body was running earlier and faster than anyone had planned for. You are, in a very literal sense, built from a process the textbook version of cosmic history still struggles to explain. Every point of light in the night sky is old news by the time it reaches your eyes, a message sent long ago from somewhere unimaginably far away. The distance and age you assign to that light depends entirely on the model used to calculate it. Change the model even slightly, and the calculated age and distance of nearly everything beyond our immediate cosmic neighborhood shifts along with it. This is not science fiction speculation. It is the direct, mechanical consequence of how these measurements actually work. None of this means the universe is collapsing, or that something catastrophic is happening in the sky above you tonight. Nothing up there is falling apart. What is actually ending is a specific kind of public confidence. The comfortable idea that this particular question was settled decades ago and simply gets repeated in documentaries, because it is obviously true. It was never as settled as it sounded. It was the best working answer available at the time, treated in public conversation like a finished conclusion instead of what it actually was, an ongoing, testable, falsifiable model, still being stress tested against new instruments every single year. And here is something worth noticing about how this story gets told to the public compared to how scientists actually talk to each other. Inside the field, researchers do not hide any of this. There are entire conferences built around the Hubble tension. Hundreds of technical papers argue over whether the fix lies in new particles, modified gravity, early dark energy, or some flaw in how distances are calibrated. None of that uncertainty is secret. But once this research filters down into a documentary, a textbook, or a casual explanation on the news, the rough edges get sanded off. Words like tension quietly become words like puzzle, and puzzle quietly becomes something people stop mentioning altogether, because uncertainty is harder to fund, harder to summarize in one sentence, and harder to sell as a finished story. The scientists are not lying. They are working inside a system that rewards confident, closed narratives more than it rewards honest uncertainty, and the public ends up with a cleaner version of reality than the one researchers are actually living inside. There is real historical precedent for exactly this pattern, and it should make anyone humble about treating today's number as untouchable. Before the 20th century, the prevailing view was that the universe was fixed and unchanging, not expanding at all. That view was overturned in 1929 when Edwin Hubble first demonstrated that distant galaxies were racing away from us. For decades after that, the accepted age of the universe still swung wildly, sometimes estimated near 20 billion years, before later refinements pulled it down toward the familiar 13.8 billion figure most people know today. Every generation of astronomers, standing at the edge of their own best instruments, treated their best current number as close to final. Every one of those numbers was eventually revised, sometimes by billions of years, as better instruments arrived. There is no reason to assume this generation is the first one that finally got it perfectly right and permanently closed the book. One especially striking case makes this concrete. There is an ancient star cataloged as HD 140283, nicknamed the Methuselah star, sitting a few hundred light years from Earth. Early calculations of its age put it slightly older than the universe itself was supposed to be, an obvious contradiction, since nothing can be older than the container it exists inside. Later refinements pulled the star's estimated age back just inside the accepted limit, but only barely, with almost no room to spare. A universe that turned out to be meaningfully older would remove that uncomfortable near miss entirely, letting even the oldest stars we can find sit comfortably inside a timeline with room to breathe. It is worth pausing here to be fair to the model everyone is questioning, because lambda CDM did not become the standard picture by accident. For a quarter of a century, it has correctly predicted an enormous range of observations, from the detailed pattern of the oldest light in the sky to the way galaxies cluster together across billions of light years to the relative amounts of hydrogen and helium produced in the earliest moments of the universe. It is not a weak or careless theory, and the researchers stress testing it now are not trying to tear it down for the sake of drama. They built careers on it. Many of them would prefer it to hold up, because a confirmed model is easier to build future work on than a broken one. The tension being described here is not a case of amateurs poking holes in something they don't understand. It is the field's own most rigorous specialists, using the field's own most advanced instruments, finding that their best framework is straining at exactly the points where it makes the boldest, most specific predictions: the expansion rate, the behavior of dark energy, and the pace of early galaxy formation. Some researchers have gone further and proposed entirely different frameworks to explain what Webb is seeing without breaking the rest of physics. One such paper, published in a respected astronomical journal in 2023, suggested the universe could be closer to double the standard age, drawing on ideas about how light might behave differently across enormous distances, and whether certain physical constants could shift subtly over cosmic time. Mainstream coverage treated the idea cautiously, framing it as interesting but unlikely, and moving on. The paper is still cited by other researchers today. The underlying question it was trying to answer, why do the earliest galaxies look far too mature for their supposed age, has not been resolved by dismissing that one paper. It has simply kept accumulating more supporting evidence from entirely different directions since. So where does that leave the honest answer to a question that sounds simple but clearly is not? How old is the universe? The truthful response, as of the middle of 2026, is that the number is not settled the way most people were told it was. Two of the most careful expansion rate measurements ever produced continue to disagree at a level scientists now describe using the word crisis. Independent survey data continues to strengthen the case that dark energy, the invisible force assumed to be a fixed constant for the last quarter century, may actually be changing over time. And Webb keeps finding galaxies in the deep past that are heavier, more structured, and more mature than the standard timeline has room to explain, with the newest research from this year making that gap larger rather than smaller. None of this is scandal, and none of it is scientists hiding the truth from the public. This is what genuinely honest science looks like at the exact moment it runs into the edge of what it currently understands. Nobody's pretending the cracks aren't there. Entire careers are being spent trying to figure out what they mean. The uncomfortable part is not that the old number might be wrong. The uncomfortable part is realizing how confidently that number was handed to you as settled fact in classrooms and documentaries and casual conversations, when the people who actually study it have been quietly wrestling with exactly this contradiction for over a decade. There is also a broader lesson buried in this story about how science actually advances, one that rarely makes it into the highlight reel. Progress rarely arrives as a single dramatic discovery that overturns everything overnight. It arrives slowly, through exactly this kind of accumulating friction. A measurement here that refuses to match a prediction there, a survey that keeps returning the same inconvenient hint no matter how the data is sliced, a telescope that keeps photographing things it was never supposed to see. Each individual result can be explained away on its own. A single odd galaxy could be a fluke. A single tension could be a calibration error waiting to be found. But when three independent lines of evidence gathered by different teams, using different instruments, testing different parts of the same overall model, all start pointing in the same uncomfortable direction at the same time, the explanation that requires the least imagination is also the most unsettling one. The model itself needs to change. Go back to where this started, to those first images from Webb, deep exposures of a patch of sky smaller than a grain of sand held at arm's length, filled with galaxies that were supposed to be too young to look the way they looked. Those images were not a glitch. They were not a mistake in the telescope's optics. They were and remain evidence. Physical, repeatable, still arriving evidence that the story we have been telling ourselves about the beginning of everything was a working draft, treated for too long like it was already the final page. That is not a reason for panic, and it is not a reason to throw away everything science has built. It is a reason to want the more accurate answer, whatever that answer eventually turns out to be, instead of clinging to the comfortable one simply because it is familiar. The willingness of researchers to keep chasing this contradiction, publishing it, arguing over it, testing it against every new instrument they can build, is exactly the process that produces better answers over time. That process is still running right now in 2026, with new data landing every few months, from expansion rate surveys refining their numbers, to dark energy maps growing larger, to Webb quietly adding fresh, hard-to-explain galaxies to its catalog on a schedule that shows no sign of slowing down. The universe you were taught about in school may not be the universe that is actually out there. The number 13.8 billion years is not disproven, but it is no longer untouchable, and the gap between the old story and the new evidence keeps widening instead of closing. Whatever the real number eventually turns out to be, it will not be handed down quietly from a textbook. It will be forced into the open, one uncomfortable measurement at a time, by a telescope that pointed into the darkest, oldest light in the sky and kept sending back answers nobody was fully prepared for, and by scientists honest enough to keep publishing what they find, even when it does not fit the story they were originally trained to tell.